All right, good morning, everyone. So we're going to continue our discussion about convolution today and see how we can do it in PyTorch. So first, we're going to look at implementing these edge detection filters, these Sobel filters. We're going to use the cameraman image again. So the first thing we have to do is we have to put our data in the form of a PyTorch tensor with the right ordering of dimensions and all that. So we can start with our image. We can extract the shape of it to get the number of rows and columns. And then remember that we have to create a batch of this shape in PyTorch. So this is the number of images in the batch, then the number of channels, then the number of rows and columns, number of pixels. So we know the rows and columns. We're just going to process this one single image, so we just have one image in our batch. And this is a grayscale image, so we just have a single channel. So now we can create this batch shape, and we can, let's see, it doesn't show how I'm getting access. Oh yeah, so we can take this image, which started out as a tensor with only 2 dimensions, and we can reshape it to a 4-dimensional tensor with these unit dimensions here. So we do that with the reshape command. Okay, so the data hasn't changed. It's just that now we're thinking about it as a rank 4 tensor instead of a rank 2 tensor. Does that make sense? Okay. And of course, this is in NumPy, so we have to bring it to the PyTorch format, torch tensor, and we finally have this. And then we can print out the batch shape, and we can see that it has the right size, and this is the original image shape in NumPy. Okay, so then next we have to bring these filters into PyTorch as well. So we can just can name one of them GX and just put in the coefficients manually. Can name the other one GY. And now we're going to put them inside our convolutional layer, but first we have to establish our convolutional layer. So we say that our model is this 2D convolutional layer. We have to tell it how many input channels. So there's just one input channel for this. But we're going to use the same layer to generate both the horizontal, both of these output images. So we're going to do that in one layer, so we're going to use 2 output channels. And the size of the kernel, we have to tell it. So we can just, this is going to be the 3x3 kernel. Okay, so next we have to get these coefficients into a convolutional layer. So what we can do is we can extract the coefficients. These would be randomly initialized by the layer. So this state dictionary is how we get things out. W and B, if you looked at the values, they'd be random. Now we're going to replace them. So we're going to, so this weight tensor is going to be, it's going to have 2 output channels, 1 input channel, and then, let's see. Oh yeah, and then the size here would be determined by our kernel. So we're going to replace, for the first output channel, we're going to replace it with GX, and the first input channel, we're going to replace that with GY. And finally, for the bias or intercept coefficients, we're just going to use zeros for those. Okay, so now W and B are correctly set up, but we have to bring them back into our model. So we say the state dictionary bias is B, state dictionary weight is W. So now they're in the state dictionary, and then we have to load that state dictionary back into the model. So now the model has the correct kernels. So the model's all set up, so we can process our data with that model, and we get YTorch, which is the output. Now if we want to plot that, we have to bring it back to NumPy, so we do this detach NumPy, and we get back finally Y in NumPy. And Y is going to be a tensor of rank 4. This first dimension, there's just one value, one image in the batch. The next dimension, the output channels, that's how we can extract the two different images, and then these are all the pixels. So we can plot these images, and we get these. And if you compare these to the results from SciPy Signal Correlate 2D, you'll see that they're identical. And this makes sense because this Conv2D and PyTorch actually does correlation, not convolution. It doesn't have the flipping and reversal. So that's essentially how we can do a simple convolution in PyTorch using the convolutional layer. Any questions on that? Okay, let's do a more interesting example where we start with a color image which has red, green, blue, so 3 channels. And then we're actually going to process it using 4 color filters. So each one of these, you can think of this as 3 kernels in one. One kernel responds to red, the other to blue, the other to green. And so those 3 kernels together are going to output channel 0. Then we're going to actually have 4 output channels. Okay, so because this has 3 colors, each of these has 3 colors. So C in is 3, but C out is 4. Does that make sense? Okay, and there's another way we could have plotted these. I could have shown you, for each of these images, I could have shown you the 3 channels independently as just a gray, black and white image, right? And you would notice, let's say in this one, that the red channel is very bright, and then in this one, the green channel is very bright, and the blue channel would be very bright, and then this one was some combination of red and blue being very bright, the other ones being pretty dark. Okay, so I just want to make sure, is it clear what we're doing here? We have a convolutional layer that has 3 input channels, 4 output channels. Any questions on that? Okay. So let's see how we do this then. So the color image, that's this one, is a tensor of 368 by 487 by 3. It starts out in NumPy. So in NumPy, this is the ordering. The number of channels always comes after the number of pixels. But when we go to PyTorch, we have to change the ordering. First, the number of channels has to come before the number of pixels, and second, we also have to tell it how many images we're processing in the batch. Here, just one image in this batch. Okay, so what we're going to have to do, as we'll see in the code, is we're going to have to reorganize our data, our image, from a tensor of this shape to a tensor of this shape. Okay, so now regarding the filtering, we have a tensor of this shape, so number of output channels, which is 4, number of input channels, which is 3, and then K1 by K2, these are going to be 9 by 9 kernels. And if you remember, this is the equation that we use for convolution. So here we have, again, number of input channels, number of output channels, and then this is pixels within the kernel. In this particular example, BM, B0. We're not using any bias coefficients. And then at the output, we're going to see, in this example, 1 image in our batch, 4 different output channels, and we'll actually get to see all the pixels in these 4 output channels. And just to give you a sneak preview, this is what the output is going to look like. Because there's 4 colors and we humans don't see in 4 colors, I can't plot those together as one image, so I'm plotting as 4 grayscale images. But that's the result of our convolution. All right. So any questions on what we're going to be doing? Is this making sense? Okay. So let's see how we do it. Okay. So when we work in PyTorch, we always need a batch of this shape. Number of images in the batch, number of channels, number of rows and columns in each image. But as we said in NumPy, we actually have a very different ordering. So what we need to do is we need to transpose these different dimensions. So if you think about when you have a matrix and you transpose a matrix, let's say I just had a matrix of this size and I transposed it, what that would mean is I'd be swapping those two numbers, right? If I have a tensor and I transpose it, that essentially means reordering that set of numbers in some way. And there's many different ways you can reorder it. It's not, with a matrix, there's only one way to do the transpose. So this is how we're going to do it. So imcolor.transpose, and then we tell it the new ordering that we want. So in the new ordering, we want the last in the 2 would index this one. We want this to come first, and then we want this one, 0, to come second, and we want 1, this one, to come third. So that's going to move the 3 to the front and give us this. Okay, so that's what this imcolor.transpose is doing. Is that making sense? Okay, the last thing we have to do is we just have to add this singleton dimension. And so we can do that using this dot reshape batch shape, because batch shape has that singleton dimension here. When we're done with that, we will have a tensor of this format, which is what we want. The very last step is to convert that tensor to a PyTorch tensor, and we do that here. So finally, we have something in the correct format for PyTorch. Okay. Any questions on that part? Okay. So now we have to work on the convolutional layer. So we're going to declare the number of input channels to be 3, number of output channels to be 4, kernel size to be 9 by 9. And then we put those numbers here when we create our model. So now our model is going to be initialized with W and B vectors of the correct dimension, and they're going to have random weights. So we can extract them using the state dictionary. We can then pull the different terms out of the state dictionary, W and B, and we can print their shapes just to check everything is correct. And yes, we see number of output channels, number of input channels, and number of pixels, and then here number of output channels for B. So everything is the right shape, but the values are not correct, so that's the next step, is to put in the correct values. Okay, so this is the most complicated part. So there's two things going on with these filters. There's what's happening spatially. So spatially, these are 9 by 9 pixel maps. But then there's also what's happening in the color dimension. Each of these has 3 colors, and there's actually 4 of those different output colors, if you call them. 3 input colors, 4 output colors. So what we can do is we can work on the colors first. We're going to make this color matrix, which is number of output channels C out in this direction and number of input channels in this direction. And this is just setting up the colors in those images. So these images are kind of special, or you could say simple, in that when you look at this image, every pixel in that image has exactly the same color. It's just some are brighter and some are darker. But the relative combination of red, green, and blue is the same in every one of those pixels. It's also the same in every one of these pixels, and it's the same in one of these and every one of these. So these are, this doesn't usually happen in an image. Like in this image, as I move across the pixels, the relative red, green, blue in each pixel changes. But these are pretty simple filters. They have constant red, green, blue ratios. So that's why the red-green-blue ratio here is just parameterized by one single number, or you could say the strength of the red is one number here, the strength of the blue, strength of the green, and that's what these are. So in that first image, you might have expected it to be like 1, 0, 0, which would mean like purely red, no green, no blue. But we're actually doing something just a little bit different. We're actually putting negative weights on the green and the blue. So it's responding to red, but it's like negatively responding to green and blue. And in this way, it happens to be 0 mean. There's nothing super important about that. We could have done this example with 0 and 0 here, but it's just showing you that there's also other things we can do too. Okay, so the next filter is sensitive to green, largest one here, but you can see there's negative coefficients for the red and the blue. The last one is sensitive to blue, negative coefficients for red and green. And then finally, this one is sensitive to red and blue with a negative on the green. So that's how we got that magenta color. Okay, so those are the color weights. Now, the other thing that's kind of special about all of these 4 images is that when you look at the sort of the magnitudes, the brightnesses, they're all identical. They're all a Gaussian pulse. It's just a different colored Gaussian pulse. So what we can do then is we can set up the Gaussian pulses separately. So here's a Gaussian kernel, just a grayscale Gaussian kernel. Basically the same thing we created in an earlier example. And so there's actually a little command here. I think maybe we might have even written this command ourselves in a few slides back. And we just tell it the number of rows, columns, and sigma controls the width of that kernel. Okay, so now we have these two things. We have the color weight that essentially tells us the colors in each of those kernels, and we have the Gaussian, which tells us the shape across the pixels. And here's kind of the coolest part, is we can create our overall 4D tensor using, with these nuns. This is the PyTorch broadcasting. So you can see what we expect out here is a tensor of rank 4. The first 2 dimensions are going to be C out by C in, and that's the size of this. The next 2 dimensions are K row, K column, and that's the size of this. And we can expand this to a 4-way tensor using the nun. We can expand this to a 4-way tensor using nun, and then we can multiply them, which is going to say that each of these total 12 kernels, 12 grayscale kernels will be Gaussian, but each of those grayscale kernels will have a particular sensitivity in terms of the colors. So, and that's what happens with this. So it's just kind of a nice slick way to create those four different color filters, if you will. And then the bias terms, zeros. Any questions on anything here? Yes.
How does the nun work to open the dimensions?
So yeah. So what nun does is it essentially, it's like forcing this to be of size 1 and this of size 1. So it's just like temporarily extending this to a 4-way tensor with whatever size is here, whatever size is here, and then 1, 1. That's all it's doing. And I think we first talked about this back in Unit 6. And if you look on that slide, there's some links to the NumPy documentation for nun. And you can find, there's a place where they describe it exactly and what it does. Actually, NumPy has a really nice document for all of this broadcasting stuff. NumPy broadcasting, it's so that explains it pretty well. Okay, any other questions? All right, so once our weight tensor and bias tensor are created, we created them in NumPy, so we have to move them to PyTorch, and then we load them into our state dictionary, and then we load our state dictionary into our model. Now our model's ready to go. We can just process our batch using our model to get our output, and then to plot that output, we have to detach it back to NumPy. And here's what we get. Okay, so let's think about what's happening. So channel 0, the output, is basically like you can say we're sliding this shape, this color shape around here, and we're looking for places in the input image which respond to that shape and to that color. Now this is a tiny little shape. It's just a tiny little 9x9. So it's just basically looking at a localized range as I slide it around. The main thing it's doing is it's looking for this red color. And when it goes through this image, it finds that this orange here actually has the most of that red color, and that's why this comes out white. White would be like a large value, black is like a small value. And you can see there's not much red in the background here, and there's not much red in this apple here, and so on. Now, here in channel 1, we're responding to this green color. So when we slide that around, we find that both of these apples have a lot of green in them. This orange has, very little green, and this has very little green as well. When we slide around that blue filter, we find that the places with the most blue are this apple, the background, the foreground, and so on. And these things don't have much blue in them. And then as for magenta, magenta seems like most in the orange in this apple, the red apple, and not these green apples here. Okay, so that's finally what we get. We get 4 channels out. Each channel is, you could say it's a grayscale image. Or sometimes we call it a heat map. And when we think about this thing together, these are these feature maps that we see when we plot Alex. So that's an example of one of these with 4 colors. And we started with our still life image here, which is a 3-color image. We did our 9x9 convolutions, and now instead of 96 like in AlexNet, we actually have 4, and now we're plotting those 4 feature maps individually so we can take a look and see what's inside them. All right, what do you think? Is this making sense? Yes?
Yeah, so how do we know that how many colors we want to select? Like you have 4 colors here, but why?
So this was just an example. So we know we have 3 input colors, and the number of output colors, I chose 4 just because, as an example. So I didn't want to choose 3 because it's kind of confusing, 3 input, 3 output. But if I choose 2 or 4, something like that, you can kind of see what's happening. Yeah, and in fact, so when you design these neural networks, those are all the choices you have to make. So in AlexNet, they chose 96. They could have chosen 128 or 64, but I'm sure they did a bunch of experimentation and they found that 96 was, somehow better. And then, they have to choose all those numbers of channels. So, when you do the project, if you're going to be designing your convolutional neural network, then that's something you'll have to choose yourself. You'll have to do experiments to figure out, for this data set, what's the best number of channels. Okay. All right, so let's look at what AlexNet learned. So AlexNet had all these 11 by 11. You could think of them as color filters because they are all working on this red, green, blue image. And so, in fact, we can plot those 96 color filters here as images. So this is all 96 of them. So, in total, so this weight tensor here had size 11 by 11 by 3. Actually, sorry. I guess the weight tensor had 96 by 3 by 11 by 11. And now I'm looking at those 96 things individually. So each of these are 11 by 11 by 3 tensors. But because we humans can see in 3 colors, I can plot each of these as a single color image. And that's what we have here. So when we look at them, we see that some of them look black and white, which means that they have equal combinations of red, green, and blue in them. But others are, very colored, which means that they have non-equal combinations of red, green, and blue in those 3 kernels. But overall, what we see is we see shapes that are kind of smooth. Well, most of them. I guess there's a couple checkerboard-like shapes, but a lot of them are smooth bumps, you could say. So this is kind of a raised edge, and then this is a sunken edge, and maybe there's another bit of a raised edge here. So there's a lot of those shapes. And they're sort of looking for, you could say they're looking for a little line that has a particular orientation, particular angle. And then some of them are looking for pairs of lines like this. And others are looking for more kind of broad bumps. Some are looking for checkered boards and so on. And then some are looking for certain color combinations like red to the northwest, green to the southeast, and so on, or blue and yellow, or just green in the middle. So these are what it learned after processing, these millions of ImageNet images for the purpose of doing image classification. So this is just what's happening in the very beginning of the network. Just trying to find these really basic features within images that it will hierarchically come up with more and more complex features as it goes through the network, but these are just the simplest ones. And when people have done experiments with mammals and they look at what happens in the V1, the early stages of our visual processing, they actually find that the mammalian brain also creates essentially filters that look very much like these. So it's pretty interesting, is what we're doing as well. Okay, so now the other thing that it's doing, as you can see, it's going from 224 to 55. So we learned that there's a couple ways to do this. There's the pooling and there's subsampling. And AlexNet is actually doing subsampling. So that means that instead of computing in this convolution, instead of computing every output pixel, it's computing every 4 output pixels horizontally and vertically. It's not even computing the other ones. It's not going to use them, so it's not going to compute them. So that's what it's doing, subsampling. So that's how it gets down to 55 by 55 images for each of those 96 channels. Okay. In later layers, it does max pooling, but in that first layer, it's just doing subsampling. All right. It does, and it uses same padding. All right, any questions on first layer of AlexNet? Okay, great. So that kind of concludes our discussion of convolutional layers. And now let's talk a little bit about how we train these networks. So we'll begin with backpropagation. We'll go through that derivation again. But then we'll also talk about a lot of tricks that are used, things like batch norm, dropout, things you may have heard about before, various buzzwords and so on. We'll talk about a bunch of those tricks. Okay, so first, let's go through backpropagation again. It's going to be very similar to what we saw in the last unit. There's just a few changes. So one change is that we have many layers here. So there's this ... just means there's many of these guys. This is the last one. You can see it ends with L. And then the second to last one ends with L minus 1, and so on. But there's a total of capital L of these layers. So this is for an L layer CNN. So we're going to be focusing on convolutional layers. So when we do our linear layers, they're going to be convolutional. If we want to think about the dense layers that we know occur towards the end of, for example, AlexNet, we can just think of them as convolutional layers with a kernel size of 1 by 1. We talked about this before. So even though we do the derivations for convolutional layers, it actually holds for dense layers as a special case. So here we're going to start with a mini batch. We know, the dimensions PyTorch uses for that, and then we end up with a scalar cost over that mini batch. And so all of our quantities now are actually tensors. So we have X, this is a rank 4 tensor. W is going to be a rank 4 tensor. Okay, B is just going to be a vector. These other guys are rank 4 tensors. And we're going to be indexing or indicating the layer with that superscript L. All right. Okay, any questions so far? All right, so let's recall first the forward pass, what happens. So just notation-wise, since our notation is always starting with A as the input to a layer, and the very first layer, what we call A0, will actually be X, the input to the network. Okay, so these are the equations that hold for layers 1 through L. So in the Lth layer, we start with AL minus 1 as the input to that layer. As you can see, this is a 4-way tensor, batch index, channel index, pixels. And we then have, since this is a convolutional layer, we have our convolutional kernel, output channels, input channels, pixels. And so then we're going to be summing across the input channels, summing across these pixel indices, and then finally adding the weight for that, or the bias for that channel. So every channel just has one scalar bias. So that's how we go from A, the input to that layer, to the scores. And then the scores, we put those through the activation for that layer. We could have different activations in different layers. And once we go through that activation, now we do our pooling. And so if you remember how pooling works, pooling, like max pooling, is actually data dependent, because we have to look for the maximum value within that channel of that batch and all that stuff. So the way that I'm representing that pooling is now the pooling can be batch dependent as well as channel dependent as well as pixel dependent. So it has, it depends both on the output pixel and the input pixel. So it has all these different numbers in it just because it's data dependent, and this way we can describe what's happening fully. And finally, we're doing a sum over all the J's, over all the input pixels, and then we get the output pixels. And that's the output of this layer, and then that becomes the input of the next layer, and so on, all the way through the network until the end. And finally, when we get to the end, we take the last score tensor, and we extract, let's say we fix I, and we put all these other dimensions into this vector here. So this is for the ith element in our batch, and we then have a cost for that. We also need to know the training labels for the ith element of the batch. So this is our cost for the ith element in the batch, and then we sum across those to get the total cost for the batch. Okay, so very similar to what we saw in the last unit. The main change is now we have a convolutional linear layer as well as pooling. Everything else, I would say, is the same. I guess Yeah, we also have, because we're doing convolutional layers, we have channels now. We didn't have channels before. Okay, any questions so far? Okay, so now we'll talk about the backward pass. So the very first thing we have to do in the backward pass is we have to do this, DJ, DZL. Okay, so DJ, DZL, I always find it easiest to focus on scalar derivatives, not, gradients. So this is going to be looking at the scalar derivative with respect to the ith batch element, the mth output channel, pixels J1 and J2 in that final, the final feature map. And so based on this equation, we can write this in terms of the non-script J, like this. So now because we're looking at a specific I, we're looking at a specific I here. And we saw this in the last unit, Unit 8. The details of this really just depend on what loss we're choosing, whether it's quadratic, or cross entropy, or what. And we have the equations in the previous unit, so that's the same as before. So we'll just assume that we can compute this, and it's computed. Okay, so now, for the rest of the backpropagation, we're going to be going, starting at this layer, propagating through that, and then once we're done with that, we'll propagate through this next layer, and so on and so on. So we're going to be doing for little l, starting at the end of the network, and then the second to the last layer, all the way up to the first. This is what we have to do. So first, we do DJ, DBL. Those are the bias coefficients in that layer. And again, let's focus on the mth bias coefficient so that this is just a scalar derivative. So when you think about that, when you think about this one single bias coefficient, you have to ask how many different dimensions in this tensor are affected by that single bias coefficient. So, okay, so if you think about it, that single bias coefficient here affects all the elements in the batch. So we have to have a sum over the batch index. But it's also applied to all the different pixels in that image, right? We just add the bias individually to each pixel. So when we do our multivariable chain rule, we have to sum over batch as well as pixels. Okay, and then, as usual, the multivariable chain rule says dj dzl times dzl dbl. And this dj dzl is something we already computed, so that's done. We just plug that in. What about dzl dbl? For that, we have to go back to our equation here. And we see dzl dbl m. That's easy. That's just 1. Okay, so that's done. Okay, next question is, what about if I take the derivative of my cost with respect to a particular element in my weight tensor? So we have to think through this again. Okay, how many batch elements does that weight tensor affect? Affects all the elements in the batch. So in my multivariable chain rule, I have to sum over the entire batch. Second, this is one single pixel in my kernel. So how many image pixels does that affect? It affects all of them because I'm sliding that around the entire image. So I have to have the sums over the pixels in this multivariable chain rule here. But otherwise, we have dj, dzl, dzl, dwl. So this we got from above, that's done. dzl, dwl, let's go back to the equation. So dzl, dwl, that's, so again, because we're going to be fixing n, k1, k2, there's only one element in this triple sum that matters, so that we can forget about that. And when I do the derivative, then all that is left is this here. So that is what shows up down here. Okay, so So that's what we need to implement. And what's cool about this is when you look at this, this is some tensor, and this is another tensor. And look at the structure. This and this show us that we're doing correlation or convolution. So when this is implemented, this essentially structurally is very similar to the forward pass. We do convolution in the forward pass. We do convolution in the backward pass as well. So if you have like a GPU that's really good at doing convolution, then not only is it good at processing these images, but it's also good at backpropagation. It's fast for both. Okay. So this is a correlation. All right. Any questions on this page? Okay, so let's go a little bit further back. So now we're going to do DJDZL, so we're going to use this as the intermediate. And again, we're going to be looking at activation element for particular batch element, particular channel, and particular pixels in this feature map here. So how many image pixels does this affect? Well, based on the equation above, that would be this equation, it's going to go through all of those J pixels. So those guys all have to show up here, and it's also going to go through all the channels. So we have this in our multivariable chain rule, but otherwise pretty standard DJ, DZL, DZL, DA, L minus 1. And okay, so how do we compute this? DZL, DA, L minus 1. This one is a little bit tricky. When you look at the form, oh, actually, no, sorry. Let me make sure I'm thinking of the right thing. DZL, DAL minus 1. Yeah, this one is a little tricky. Okay, so we want to do DZL, DAL minus 1. But we don't want these J plus Ks in there. Ideally, when we looked at this would have, let me just call it like, maybe I'll call it like L1, L2. And then it would be very clear how to do the derivative. But because we have these in here, we actually need to rewrite this a little bit. We're going to have to do a variable substitution, right? I define this, let's say, as L1. I define this as L2. And then I'm going to rewrite this in terms of that definition. So let's see. So K will be L minus J. So this would be like L1 minus J1, L2 minus J2 here. And once I rewrite it this way, then the derivative is easy to compute. You're just going to have this. And then that is essentially what we get down here. Notice the minus signs that we just saw. Okay, so like I said, getting this involves doing a variable substitution on that equation above. You'll get a chance to practice this in the homework. See how exactly that manifests. Anyway, once this is done, as you can tell, this is once again a convolution. We have the minus signs here, so it's actually a true convolution. And it's not a big deal, to do that, to handle the minus signs. Basically, again, backpropagation is a convolutional type operation. And then the last part is DJ, DZL minus 1. So we're going to go through the A's as the intermediates. So we're going to have DJ, DA minus 1, AL minus 1, DA, DZ, like this. And then we have to figure out, how many different things to use in our multivariable chain rule. In this case, it turns out to be K1 and K2. So back in this equation, the notation has changed a little bit, but we have to basically we have to use both of those sums. So, so here, this term we just computed here. This is the new term, dA L minus 1, dZ L minus 1. This one is not too bad. We look at this equation. So we're doing d this, d that. So the first thing you'll see is we'll need to take the gradient or the derivative. This is an element-wise operation that applies. So we'll just take the derivative of this. So we'll call it HL prime. And then we'll just multiply by this and sum over that. So that is what's happening here. So here's the prime, here's the derivative. And this is just the pooling operation, just essentially a linear operation. So, yeah, essentially that's it. We've gone through the whole layer here, and then we just repeat with the next layer and so on all the way back through the network. So once you get the hang of backpropagation, it's not really super difficult. It's just a procedure. It's a very organized procedure that that helps us, do all these kind of complicated derivatives, but in a systematic, organized way. Okay, any questions on the backward pass? Backpropagation in CNNs? Okay. All right, well, let's talk about other things that are important for training. So, so as we saw, these CNNs involve millions of trainable parameters. Not only that, but in order to train all those parameters without overfitting, you need huge data sets, maybe millions of images. And you simply can't do this with a conventional processor in a reasonable time. So you need to accelerate it somehow. So, back about 10 years ago, people realized that a lot of the computations done for graphics processing in these GPUs are actually very similar to the sort of things that we need to do for convolution and in our deep learning. So they started to kind of hack those and use them for deep learning. And now there's, it's a huge market of these GPUs that are specially made for deep learning rather than for video graphics. And if you really want to get serious with machine learning, you somehow need to use these. So you can buy a computer, that has maybe one or two of these cards in them. Depending on which card you get, maybe with a consumer setup, I'm writing 3K here. Probably it's more like 4 or 5K today, but you can buy a nice machine for that price. Now, if you want to buy a machine that has 4 or 8 high-end GPUs, now it's about 10 times as much money. These days, it's actually probably closer to 50K. But what's nice about using many GPUs is that at least up to a few GPUs, the performance really does scale linearly. So here's an example where we have, this is execution time, so basically smaller is better. And here's the number of GPUs, 1, 2, 4, and 6. And so you can see when I go from 1 to 2 GPUs, my execution time does drop by a factor of 2. In fact, even a little bit more than 2 here. When I go to 4, it really does drop by a factor of 4. And okay, then things start falling off. When I get to 6, my performance is only like 5 times as fast as a single GPU. But at least there's a pretty good scaling here. And in terms of computation time, you can see it goes from 180 seconds down to like 40 seconds. So this can make a big impact on your training. And if you're you're at Google and you have access to all their resources, then you can afford to run hundreds of GPUs in parallel and work on massive data sets and so on. Okay, so what are other things that matter when we train? So essentially, we know that the learning rate is really important. We talked about choosing the learning rate way back when we talked about convex optimization, and we had the Armijo rule and other ways to do it. But actually, when we talk about deep learning, the learning rate is, in some sense, even more important because the situation is different. Now we're working with non-convex optimizations. And if you use a really small learning rate, what that means is you're going to start somewhere, usually start with a random initialization, and with a small learning rate, you will just converge to the closest minima to which you started, right? You'll just locally converge there. And often that's a bad minimum. You'll get stuck there. So basically with CNNs, small learning rates cause convergence to bad local minima. So this is an issue. So essentially what we want to do with our learning rate, at least at the beginning, is we want a large learning rate to jump out of the bad local minima. We want to escape them. And we want to hopefully jump into a much better local minima. It's impossible to guarantee that we will jump into the Bayesian of attraction of the global minima, but what people have seen is that there's maybe lots of these good local minima that are equally good or nearly equally good. So we want to jump into one of those. And so essentially the way we do this is we want to use a fast learning rate, at least at the beginning, to try to jump into a good one. But then once we're in this Bayesian of attraction of the good one, if we keep our learning rate large, then we will never settle to the bottom. We'll just be jumping around wildly within that. So later we want to reduce our learning rate so that we get finally converged to the bottom of this basin with the good local minima. So for that reason, we need to schedule our learning rate. We need to say, I'm going to start, let's say, big and make it smaller. So basically, that's the main idea. First, we use a large learning rate to escape the bad local minima, and then later we use a small learning rate to converge to a good local minimum. So here you can kind of see the idea. If you, let's say, started here with a really small step size, you would just converge here and you'd stay there, or maybe you converge here and stay there. We actually want to sort of jump out and land in this one. But then we don't want to be jumping around here. We want to settle to the bottom, and for that we need to reduce our learning rate so that we can finally settle down there. So this is, of course, just a very stylized illustration, but that's kind of the main idea. So any questions on that? Is that pretty clear? There's another way to try to jump out of this local minima, which is to use momentum. So momentum is, as it sounds, it just says like if your learning rate, if your gradient descent algorithm is moving in a certain direction, it has some momentum, and it continues to move in that direction in future iterations, even if the data tells it, maybe not to. So it has this momentum. And that momentum can also push you through and over these bad local minima. So there's a number of algorithms that are popular to use for these deep neural networks. Like ADAM is probably the most popular one, and ADAM uses various tricks internally. It uses momentum and other things, as well as adjusting the learning rate. And it has a nice combination of tricks, and it seems to work pretty well in general. But it's not the only one that people use. Okay, let's see. So here's another figure which also shows this. So this is a plot of the loss versus the learning rate. So this would mean that essentially they would select a learning rate. They would then run the optimization for a while until it sort of settled out. And so if you use a very small learning rate here, you can see that the loss you get is pretty high because you're stuck in a local minima. Once you increase your learning rate into this range, you can get to a good loss. So this seems to be a really good range to get losses down here. Now, if you really push it and you use a very large learning rate, as you can see, things go kind of crazy and it's now too big. So here is where you can see the importance of using a good loss. So actually, I might have misspoken. I think maybe this is, I can't remember how many iterations they use when computing this plot. Maybe they only used a few iterations. Maybe they didn't go until convergence. I think that's probably what they did. They used a few iterations, like maybe 10 or something, and they showed what happened after a few iterations. Okay. So there's many of these different schedules. We talked about, just essentially starting big and then going small, but there's a lot of other ones too. And some of them are adaptive. Some of them look to see when, let's say, your loss seems to have settled out, and then it says, okay, let's decrease the learning rate to try to make it smaller. And if you set it up incorrectly, it's, maybe it will be in this region, and it will say, okay, things have settled out, let's make it smaller, and that won't help at all because it's already too small here. So you have to be careful when you implement these schedules. But basically, so here's a few of them. Like there's stepwise, which basically goes every so often. It goes down and it stays, and then it goes down. There's exponential, which just kind of smoothly decreases. Now some of them actually are periodic, like cosine goes high, low, certain number of times. Cyclic is another periodic one. And there's this one cycle that claims that it's the best. So here you basically start at a medium learning rate, then you ramp it up to a very high learning rate to try to jump out of these bad local minima. Hopefully you've gotten to a pretty good one, and now you gradually ramp the learning rate down. Hopefully now you found a great one, and now you make it much smaller to try to settle within that learning rate. And this paper, claims that it can converge extremely fast relative to other techniques. This is the one cycle. So you can click on these links here if you want to read more. All right, so that's learning rate schedules. Any questions on these? Okay, a lot of choices here. So we're out of time for today. Next time we'll talk about other tricks, batch normalization, dropout, data augmentation, various other things that are all very important to getting these deep networks to train correctly and quickly and so on. So I'll see you guys on Friday.